Good morning, good people. Can you hear me? I can hear myself, which is not a good thing. Anyways, good morning and welcome to the IETF and welcome to ICCRG. If you don't believe you're here for ICCRG, stay on anyways. This might be more interesting than anything else you're going to go to. Before we start, I need the standard things. I need JavaScribe and I need a minute taker. Volunteers. Come on. I can start naming names. Gauri, you're looking at me like you want to do something.
Jana, I'll take the minutes, but I don't have a Java client.
What did you say, Andrew?
I said, I'll take the minutes, but I don't have a Java client, so someone needs to JavaScribe.
Thank you. Andrew's going to do minutes. Jabber. Thank you, sir. So we've got a JavaScribe and we've got minute taker, so we can move on. So we have a pretty packed agenda. Let me see, how do I do this? There. But before we start, we will just briefly, I will flash you the Notewell. Very, very briefly, we follow the IETF IPR disclosure rules. And if you do not know what the Notewell is, you should go read it before you come up to the mic and say anything at all. There's also privacy and code of conduct, which again, I will not go into right now, but you're welcome to read it. The slides are available online and the code of conduct is available online at that URL. And the goal of the IRTF, just to be very clear, we do research, we don't do standards development. So if you're here to push a standards track RFC, you're in the wrong room. But if you're here to hear about research ideas and not just standards work, then you're in the right room. And there's our agenda for today. So we're going to basically, we have a fairly packed agenda. And I'm not going to walk through the entire agenda, but we're going to try to get done on time here. So to the speakers, please come up just as your talk is about to start, and please make sure to stick to the allotted time. And that includes me, so I'm going to go through this fairly quickly. The first thing to note here is we have two side meetings. We couldn't really bring them into this meeting, but they are very relevant and you may be interested in them. So do go to them if you think you are interested. The first one is on data center congestion control, and Paul Congdon is organizing this. Paul's there raising his hand. And please ask him, speak with him if you have any questions. Otherwise, those details are still correct, Paul? Okay, lovely, thank you. So that's tomorrow morning in room VIP A, early in the morning, the side meeting time slot. And then we have L4S on Thursday in this very room at the same time at 8:30 in the morning. Bob, are those details still correct? So this will basically be an update on L4S. Yes. Oh, L4S and okay, TCP Prague. It's about TCP Prague, not about L4S, not just L4S. Yeah, okay. But it's L4S and TCP Prague.
Yeah,
so,
right. The details are that the L4S is mostly in the TSVWG meeting on Thursday. This side meeting is mostly TCP Prague.
Fair enough. Thank you for that clarification, David. And that's happening Thursday in the morning. So again, these are very relevant to ICCRG. So we just don't have enough time in here to do all of these conversations. So these side meetings are, you're encouraged to go to them. I will be there. And with that, I'm going to start off on just one topic. I'm going to spend at most 5 minutes on this. We had started a conversation last time. I'm trying to figure out how to do this. Should I go to full fit to page, maybe? Okay, that works. I had broached the topic of doing documents in ICCRG, publishing documents through ICCRG, adopting them in ICCRG. I've had a number of conversations with various folks since then, and I'm basically here to say now that we will start adopting documents in this research group. I intend to use discretion and the RG's guidance in proposing what documents make sense. But that's the goal is to adopt and publish documents here. We've done this way back in the past. We're going to start doing it again. What does it mean to adopt documents? Well, broadly, the document is a reasonable fit for what we do in this room. And by what I mean by what we do in this room is not just if it fits the letter of the charter, but if there's energy in the room and if there's just the right sort of audience to do this work or look at these documents. Typically, any congestion controller that fits in internet-like environments is an absolutely wonderful fit, for example. But we need to see author engagement. We need to see author engagement with the research group and to show that there's interest in continuing that engagement to be adopted in this research group. And again, I intend to use discretion and research group guidance in determining relevance here. What does it mean to publish a document? It just means that the research group thinks the document is in good enough shape. Yes, this doesn't seem like a very formal process, but that's by design. This is not intended to be a heavy process. This is not the IETF again. I expect to call upon the RG, folks in the RG for reviews and for other decisions, and we will figure this out as we go. I have faith in the community here that we can make this work. I feel great saying this, by the way. This is a good meeting to say this because I feel like I'm handing off this, I'm doing this thing from up on high, looking down at all of you. I will decide. But this is the plan going forward, is to publish documents in ICCRG. And starting off, I'm going to propose adopting the following documents. We will hear about them today. The first one is LEDBAT++. The second one is RLEDBAT. If you haven't read these documents, please do. I think they are fairly good, and I think LEDBAT++ is actually, I'd say it's almost an update to LEDBAT, and it's a very important update to LEDBAT itself. So I'm going to propose this. I will also send this out on the mailing list, and will adopt it unless I hear somebody yelling and saying this is a terrible idea. That's the plan going forward. With that, well, any quick thoughts? I give you 30 seconds. And your 30 seconds are up. Thank you, Gauri. Sorry, go on.
Gauri first. I'm cold. I can't run quick. I think this is a good idea. I like this, and these two documents fit well because they are more conservative than other transports. Therefore, they definitely fall within something that could be done in a research group. Other things we might have to tread carefully on, and I guess we'll figure that out as we go on. But these two documents seem like good candidates for here to me.
Yeah, I think we will have to figure this out as we go.
So question is the, Martin Duke, F5, is the desired outcome of these documents to produce informational RFCs or something else?
Yes, I would think so. I don't know. Can we publish experimental RFCs here? Anybody know? We can't do that here, right? Who says we can? Andrew says we can.
Hi, Colin Perkins. Yes, Colin. You can publish experimental or informational RFCs.
Thank you, Colin. That's the voice of authority there. So yeah, I'd be interested in experimental, but that's what I'm going to be pushing folks for anyways. Thank you for that. With that, I am going to move on with the agenda. Again, this is the agenda. Praveen, you're up first. We're going to talk about LEDBAT++. I'm going to get the slides up.
Morning, everyone. Can you hear me?
Ravi, see if that works. Doesn't work? That's fine. I'll move the slides forward.
Morning, everyone. I'm here to talk about leadbat++. This is now a draft. If you haven't read the draft, there's version 01 that was published recently, so please read it. Leadbat++ is a less than best effort congestion control. So the goal is to use unused capacity, but quickly yield to foreground flows. Example workloads include operating system or application updates or backup replica sort of workloads. Next slide, please. This slide is a summary of leadbat++. The original RFC 6817 has a bunch of problems which were found in prior research as well as in our efforts to implement the RFC in the Windows operating system. I'll quickly walk through the problems and the mechanisms that leadbat++ proposes to fix those problems. One-way delay measurements are hard in practice. For example, in TCP, the clock frequency is not known of the peer, as well as there is a clock drift problem. leadbat++ uses RTT. There's a downside, which means on the downlink, you may measure congestion and react to it. But because this is less than best effort in practice, this doesn't cause problems. There's a latecomer advantage problem. If there are multiple flows already in the bottleneck link, a latecomer leadbat flow would end up getting more than its fair share. leadbat++ introduces two mechanisms to address this problem. One is multiplicative decrease instead of additive decrease during congestion avoidance, as well as initial and periodic slowdowns. The original RFC said that natural gaps in application traffic would allow leadbat to measure the base delay, but that doesn't happen in practice. So leadbat++ immediately after slow start would enter a slowdown period, and then would enter subsequent slowdown periods with a goal to sacrifice throughput of to be at least 90% of standard TCP when there is no competing traffic. There's an inter-leadbat fairness problem as well. This is related to the latecomer advantage problem where you can't measure the base delay, but although the queue is stable, the flows don't fair share. The leadbat++ introduces multiplicative decrease to solve this problem. The original RFC does not specify slow start in very great detail. There's two things that leadbat++ does. It does slower than Reno ramp up during slow start, and it also does a variant of high start to exit slow start when it senses delay increase on the bottleneck link. There's also a latency drift problem when you let connections run for a long time. There's a ratcheting effect where the measurement of the base delay keeps increasing, and that causes us to keep increasing latency on the link. Initial and periodic slowdowns help address this problem. There's also a low latency competition problem. If you have a bottleneck link where you can't reach target delay, for example, if the buffer is too small, that causes leadbat to basically just compete with standard TCP on the bottleneck link. So slower than Reno increase during congestion avoidance addresses this problem. There was, on the mailing list, there was a problem that was brought up. I think Neat Cardwell brought this problem up where what happens when there are multiple flows or large number of flows on the bottleneck link? Do we see a ratcheting effect problem or not? So we actually did this experiment recently. So this is a 100 millisecond RTT link. We actually changed the target delay to 100 millisecond for this experiment. But yeah, the results are similar with the default of 60 millisecond. And this is a 10x BDP bottleneck buffer. So even with the increasing number of connections, we see that the latency remains near target, at or near target. So when we look at traces, there's two reasons. One is when the new flow starts, even though the slow start is slower than Reno, it still causes a delay increase. And that causes other flows to back off. And then the newcomer flow would immediately enter its slowdown phase, allowing all the flows to measure base delay. We find that all the flows are able to successfully measure base delay. There is another experiment. This is with both 1x and 10x BDPs, again, with large number of flows. As we increase the number of flows, we find that things mostly stabilize around target. So this is with 100 millisecond RTT and the default 60 millisecond target. So we would like to experiment more. There was a suggestion that we use BBR's probe RTT phase and see how that does in comparison. That would be a very interesting experiment to do in the future. But currently in practice, we don't see a problem. What are the changes since the first draft? So I rearranged some sections to make readability easier. And thanks to Marcello's review, so I fixed all the feedback that he gave to make the text better. The multiplicative decrease cap was not specified very well. So the intention is to basically ensure that we never react more than what Reno would do if it sees a loss signal. So the delay increase signal, the worst case decrease, even with multiplicative decrease, would be half the congestion window. Remove the reduction factor just to simplify. So if the reader has read LEDBAT, we just use the gain parameter now. One of the requests has been to make the document standalone. Currently, it's a addendum on top of the original RFC. So the goal is to make the document standalone so that any implementer could just read this RFC and be able to implement the algorithm. We also want to add pseudocode so that it makes it easy for implementers. So my request to folks in the room would be, please review this draft. I think like less than best effort congestion control is extremely important. So please review this, please provide feedback. If you could implement this and do some experiments on your own, that would be great too. Any questions?
Jake Holland. I was curious whether you had a chance to examine the impact of AQM or of FQ systems on this strategy.
We have not. So I called that out in one of the prior presentations. It's also an active area of research. I think like both testing with AQMs as well as newer congestion controls like BBR, they currently are testing is limited to Cubic and Reno. So testing with other delay-based congestion control algorithms which are aggressive would also be, I think, part of that future work.
Okay, thank you.
Any other questions? We have a couple of minutes. All right.
Thank you.
Thank you for your presentation. Marcelo. There we are. Ah, shoot. Damn sensitive thing.
Good morning. I'm Marcelo Bañulo, going to talk about the receiver-driven LEDBAT. So I already presented this in the last IETF. So basically, this is an update of the changes that I done in the draft. So if you remember, LEDBAT is a set of mechanisms that allow to run a less than best effort congestion control algorithm at the receiver in order to throttle the control the sender's rate, right? So in the original document, I mean, in the version 0 document that I presented last time, the document contained both the mechanism to implement this in the receiver and the congestion control algorithm. The congestion control algorithm is now moved to the LEDBAT++ document that Praveen just presented. So in this document, we only kept the set of mechanisms that allow the receiver to exert control over the sender's rate, right? So in particular, in this document, we kept how to use the receive window, how to manage it safely in order to avoid window shrinking, handling the window scale option and this type of things in order to control the sender's rate, right? In addition, we work out the different mechanisms in order to feed the information that the congestion control algorithm needs, including the RTT measurements in order to estimate the queuing delay and the detection of retransmissions at the receiver. So basically, the input that the congestion control algorithm will receive will be some form of RTT measurements, delay measurements, and some form of loss transmission detection. So the changes since the 0.0 version is we remove all the part of the congestion control algorithm. We define so that our LEDBAT is compatible with any less than best effort congestion control as long as it uses some form of delay estimation and or packet losses in order to work. We currently are referring to LEDBAT++ or any other congestion control that uses this type of signaling. We could point to LEDBAT if we consider that using LEDBAT with RTT instead of one-way delay makes sense. Considering that LEDBAT++ is essentially an upgrade on LEDBAT, we believe that this may not make a lot of sense, but we could do it if people feel strongly about LEDBAT. And regarding our LEDBAT implementation, we are currently working. We had an implementation. We presented some results in the last IETF. We're now working in order to make it perfectly aligned with the LEDBAT++ latest version that Praveen just presented. This is ongoing work. We hope to be able to present results in the next meeting. And we also became aware that Apple have a receiver-based less than best effort implementation that is available is open source and available here. It seems somehow aligned in the sense that it uses RTT, it uses timestamps and receive window, basically the tools that we are describing in the draft. But it would be interesting to actually have some input from Apple to see if they actually are aligned to what we present here, and if not, to be able to align properly. The less than best effort congestion control algorithm that they use clearly it seems different than LEDBAT++, but as I said, our LEDBAT is compatible with different congestion control algorithms, so this would be an example of that. Next steps would be very useful to have reviews, comments from the research group, and feel free to contact me if you have further questions or comments. And with that, I'm available for questions, or I can leave.
Questions, folks? Come on, it's Monday morning. Do it at the mic is all I'm saying. Some engagement, people. Well, I actually do have one question for you, Marcelo. Have you considered expanding this to, the mechanisms would just be slightly different, but I think the concepts still hold for Quick?
Yes.
Do you plan to write that in the draft, or?
Do you think in this particular draft?
Yeah, I'm asking.
I was thinking to, once I'm done with this, do it in a different document, but if you like.
That'd be fine too.
If you want me to do it in this document, I'm happy to do it.
It seems reasonable to do it if you're going to cover both TCP and Quick in the same.
Okay.
If it's possible to do it. I don't think the differences should be that much.
Okay.
But
I can look into that. Yeah.
Yeah. Look at it. If it becomes big enough, it might be worth separating it out.
Okay. Yeah. Sure.
Yeah. Thank you.
Gori Fairhurst just asking about what you actually said at the mic. Were you asking about strange echoes? Were you asking about whether this document could describe a method that could be applied to Quick, or were you saying the document would include a mechanism that described how it applied to Quick? I see the two as quite different.
That's fair. I was asking how you would apply. So the mechanism itself is not an on-the-wire change. It's entirely a receiver-side. It's management of the receive window, or in the world of Quick, it would be how you advertise flow control credit. And so it would be slightly different in the sense that you're not just talking about modulating the window, but you're talking about modulating the size of the credit that you're going to advertise. And there is no equivalent. You can actually shrink effectively. So that gives you a degree of freedom that is available in Quick, because what I mean by shrinking is you advertise lesser credit in the future, right? Because you can actually shrink the window. So if that, that's what I was asking. Okay. Right. The way it applies to Quick would be slightly different.
So if I understand that, that means this is a mechanism. And you're not going to describe the protocol, but you're going to describe the mechanism. Is that
Fair
what
enough.
you were talking about?
Yeah. So maybe then what I'm asking for, thank you for teasing this out, Gori. What I'm asking for is how would this apply to like a credit-based flow controller as against a window-based one?
Okay.
And that's the difference I'm looking at.
That seems clear. Thank you.
Praveen from Microsoft. I do think that both of these RFCs are sort of transport agnostic. There are certain like transport mechanisms we're using to communicate information, as you point out. But yeah, I think they could be written in a way that they could be applied to both TCP and QUIC.
So that's true, but there's the avoiding of the window shrinking, right, which is very TCP specific. It's very ecosystem specific too. No, that's not applicable to QUIC.
Possibly not, but I don't think it's illegal to shrink.
It's what's not illegal? It's not illegal to avoid it, certainly, but I'm saying you have that degree of freedom if you want it.
Right. Okay.
Michael Welzer. I'm wondering about the window shrinking thing. Is that like what? I mean, I understand what it is, but I don't know what would current TCP sender applications do if you would submit the window that is too small and you would actually shrink it. They might just ignore it, right? Because they have to have a way of handling it on the sender side anyway, if that happens. Or would they send a reset? Or does anybody know?
So if you as far as I can tell, there are some situations where window shrinking is unavoidable. When you're using very large window scale, for instance, that the granularity of the window that you are able to announce will result in window shrinking. So I understand that implementations usually can handle window shrinking without losing packets, but that's what I think Praveen told me.
So Gori Fairhurst, not answering the question directly, but saying that I'm going to talk in a side meeting on QUIC for satellite later in the week, and one of the things I'm going to talk about is the way TCP windows are managed in BSD, using receiver window advertisements and how you grow and shrink the receiver advertisements and how that relates to what QUIC does. So this is an area where, yes, you can change the receiver window and it doesn't have an impact. Maybe that causes you to send more than you expect and it ends up being ditched or whatever. But this is a mechanism that does work in real implementations. And talk more to me if you wanted to find out what I was saying.
Nothing else to say.
All right. Well, thanks, Marcelo.
Okay. Thank you.
So these are the two drafts that we are planning to adopt. And if you have any thoughts, please send them to me or send them on the list. Like I said, I will send out an email again to the list after this meeting. And I see Neil's already there. Hang on.
Hi there. Okay.
Slides up.
Can you guys hear me?
Yes, we can hear you.
Okay, great.
And your slides are up. Go, Neil.
All right, great. Hi, my name is Neil Cardwell, and I'm going to talk today about, with a brief update on BBR version 2 work at Google. We think of BBR 2 as a model-based congestion control, and today I'm going to focus on some recent performance optimization work that we've done. This is joint work with my colleagues at Google, Yu Chang and Sohail, Priyaranjan, Yusuk, and Kevin, the QUIC folks, Ian, Victor, and Bin, a summer intern I had this year, Luke, and Matt Mathis, and Van Jacobson. I'm hearing a substantial echo on my end. Are you guys okay?
Yeah, we are fine. We are
Okay.
also hearing echo, but that's just a function of the room.
Okay, great. All right, next slide, please. Yeah, so just a quick outline. I'm going to talk for a while about the performance optimizations I mentioned, and then I'll give a quick rundown of the status of the BBR version 2 code and the deployment at Google, and then wrap up. Next slide, please. So yeah, performance optimizations. Next slide. So what are we doing here? What's the goal here? Well, we basically want to ensure that BBR version 2 gets to a point where it's doing a good job as a general purpose congestion control for both TCP and QUIC for the environments where those transport protocols are used today. So that means LAN and WAN networks, data center networks, VM guests. And we want to get to a point where it's a good drop-in replacement for the predominant algorithms used today, so Reno, Cubic, DCTCP, and we want to make sure that it's providing performance improvements across all of those environments and has acceptable coexistence properties when it shares with common congestion control algorithms like Reno and Cubic. And of course, as a stepping stone to number one, we are deploying BBR version 2 for all the TCP and quick traffic at Google, and we are working on that as we speak. And as part of that, of course, that involves a fair amount of testing. We basically want to ensure that BBR is doing a good job on both the production workloads we see at Google and a wide range of test matrices in synthetic or lab tests. And we want to make sure it's doing at least as well as Reno and Cubic and DC-TCP. Next slide, please. So I mentioned some tests of production workloads at Google. So what's that? So at Google, we do a fair amount of testing on our production kernel changes. This includes TCP, loss recovery, and congestion control, including BBR changes. And there's a fairly rigorous suite of application benchmarks that we apply. Obviously, web search is included, but also databases and storage. And we look at a fair number of scenarios, and not just sort of simple bulk transfer dumbbell tests, and not just looking at only traditional congestion control metrics like loss rate or throughput, fairness, queuing delays, and so forth. We also look a fair amount at CPU usage and median and tail RPC latency. And why do we do that? Well, when you operate these things at scale in production environments, of course, the details matter a lot. And in particular, one of the important details that doesn't always get as much attention as it should is CPU usage and the sort of contributing factors, including data packet send rates, acknowledgement rates, offload burst sizes, interrupt rates, all the things that feed into CPU usage. And in addition, there are a lot of sort of tricky and stressful scenarios that are important to test, like when you have thousands of flows coming from a single sending host or sharing a small BDP in a data center-like environment. Those are also important to test. And as we've been running BBR version 2 through these kinds of tests at Google, we've developed a number of performance improvements to tackle various issues that we've seen in these tests. And so I'll go through these in a little bit of detail, but just to give a quick summary, I could say that basically the first two improvements are in order to match the CPU usage for Reno or a Cubic or a DC-TCP. And number one, we developed a fast path for BBR. And number two, we did some improvements in the TSO auto-sizing calculation. And then the third improvement was to fix a sort of interesting issue we uncovered with the Linux TCP receive code path. And for that, we've developed a mechanism that generates faster ACKs. And then finally, the fourth one is to enhance BBR version 2 so that it gets better performance than the widely deployed algorithms like Reno and Cubic and DC-TCP, in the sort of interesting case where there are more flows sharing a bottleneck than the BDP of the path expressed in packets. All right, next slide. So the first improvement that we worked on was a fast path for BBR. So why did we do this? Well, much of the traffic in the real world is application limited. So web transfers, RPC traffic, adaptive bitrate video. And if you think about it, Cubic and Reno and DC-TCP, when they're not receiving ECN or loss signals, they take essentially a fast path when they have application limited traffic. The first couple lines of most of them basically say, if the flow is not currently C1 limited, then let's return and not do any of the other processing that we might normally do for the congestion control. The problem here is that BBR, when run on these very simple application limited workloads, ran into CPU usage issues and even throughput regressions on some of these simple application limited workloads. And why is this? Well, thus far, the BBR code base has tried to prioritize simplicity and basically ran the entire algorithm on every ACK. So that means updating the entire model of the path, updating the probing state machine, and then adjusting all of the control parameters, the pacing rate, congestion window, offload chunk size. And this was causing up to sort of 2 to 5% CPU and throughput regressions on some of these synthetic tests in these workloads. And to tackle this, we basically constructed a fast path for BBR, where the idea is that we only run the portions of the algorithm that are strictly needed based on the properties of the information being conveyed by a given acknowledgement. And this resolved those CPU and throughput regressions without sacrificing throughput or latency. Next slide, please. So we also worked on some improvements in TSO auto-sizing. So what is TSO auto-sizing? So in high-performance transport stacks, often they achieve a very big performance improvement by bundling together consecutive segments into a single unit when passing them down to lower layers like the IP layer and the NIC driver. And in particular, the core Linux TCP stack has, for about 7 years or so, used a TSO auto-sizing algorithm that adapts the offload chunk size largely based on the pacing rate. And it goes something like this. So the core TCP stack computes a pacing rate, and whether that's used for pacing or not, it still uses that pacing rate for the offload sizing decision. So it computes the pacing rate as some constant scale factor times the congestion window divided by the smooth round trip time. And then it takes that pacing rate and it calculates how much data it thinks would be paced out in 1 millisecond. And then it applies a floor of 2 segments and a ceiling of 64 kilobytes that's determined by the offload mechanism itself. And an interesting thing happens if you have a workload where the sender host is the bottleneck for a large number of flows. And in that kind of scenario, because the sender host itself is the bottleneck, there tends to not be any ECN or loss signals that the senders get. And so with an algorithm like DCTCP or Cubic or Reno, the CWIN can be surprisingly high in these cases, which then generates a large pacing rate and then a large offload chunk size. And that large offload chunk size allows very low, very efficient CPU usage. And then the problem is if we take a BBR scenario where we have a large number of BBR senders and they try to reuse this auto-sizing algorithm, now BBR is computing its pacing rate based on its estimate of the flow's fair share of the bandwidth coming out of that sender host. So if you've got thousands of flows, the fair share for a given flow is quite small, so BBR was choosing small offload chunks and using a lot of CPU. And so to solve this issue, we developed a mechanism that adds a term into the auto-sizing calculation that is a function of the minimum round trip time, so that as the minimum round trip time grows, the size of the offload budget that is added for the minRTT falls off rapidly. But for very small minRTTs, there is a considerable budget that's allocated for the TSO offload size. And you can see the exact formula there. And you can read the code for the details and the constant. Next slide, please. So the third issue that we tackled was and it's sort of an interesting issue involving the specifics of the Linux TCP receive code path and the delayed ACK logic. And DCTCP and BBR v2 both have a nice property where they emit an immediate ACK when the incoming stream of congestion experience bits change. But that mechanism doesn't always save you, because if you're under heavy enough congestion, then there's continuous CE marking and that mechanism doesn't kick in. So what can happen is that you can actually get into trouble as a Linux TCP receiver, because the details of the code for the traditional TCP ACK every other packet mechanism are actually a little surprising. And there are actually 2 conditions. The first one is what you might expect, which is to say, if more than one MSS has been received since the last time we sent an ACK, then that condition needs to be met. But it also has to be the case that the next receive window that we're about to offer is at least as big as the previous one. And the problem you get into is if the receive window stops growing, this causes check number 2 to fail, which causes the receiver to wait until the application actually reads some data out of the receive buffer to allow the receive window to advance and then trigger an acknowledgement. And this was actually, this sort of surprising detail was actually causing 2x higher P99 RPC latencies with sustained congestion in some of the tests we were running. And as a solution, what we've done, at least thus far, is to just remove check number 2. And this has taken care of those RPC latency issues. And we should say that if this works well in practice as we deploy, I think we'll propose this as a general fix for the Linux TCP receive code path. Next slide, please. So this is just a quick picture to give a better sense of what's going on there, because I know the text doesn't make it entirely clear. So here we have a picture that's a time sequence diagram of one of these scenarios. And you can see at the beginning of the connection, the receive window is opening up. You can see that as the receive window, the yellow line is growing further away from the ACK line, the green line. And during that phase, the receiver is allowing itself to acknowledge immediately, just giving a high throughput, which is reflected in the high slope of that line. But then as soon as the receive window stops growing, the yellow line sort of plateaus. You can see that the ACKs are all of a sudden very delayed because the stack is suddenly waiting for the application to read some data before it sends an acknowledgement. So that's just an illustration of an example of this. Next slide, please. So finally, the final mechanism I'm going to talk about is some work in progress that we have to reduce the queuing that we see when we have lots of flows. So next slide. So what's the scenario we're talking about here? So this is a scenario that's been documented and talked about for quite a long time. I think it goes at least as far back as Robert Morris's paper on TCP behavior with many flows in 1997. And maybe there are earlier papers as well. But the basic issue is that when you've got many flows and a low BDP, then most existing widely deployed congestion control algorithms like DCTCP, Cubic, Reno, and BBR thus far tend to run window limited. And they're going to have a standing queue when the number of flows times the minimum congestion window of those flows is bigger than the BDP. And the problem that you then get is that there's a standing queue that's basically that budget of the aggregate in-flight, the number of flows times the minimum C-wind, minus the bandwidth delay product, and that can be fairly substantial. And just as an aside here, to give some sense of scale, the BBR minimum C-wind, aside from RTO recovery, is 4 segments, and that's to avoid stop and wait behavior with TCP's ACK every other packet policy. So the diagram here sort of gives you an intuition about what's going on. You can sort of see that the queue of excess packets here is building up at the bottleneck due to the aggregate in-flight being larger than the BDP of the path, and all of these flows running window limited. Next slide, please. So the solution that we've been investigating is to improve BBR's use of ECN and loss signals to make sure that we do a better job of adapting the pacing rate to match the available bandwidth. And so there's sort of 2 core pieces of this. The first is a multiplicative decrease in the pacing rate and in-flight data when we see ECN marks as well as loss. And that allows us to sort of quickly match the available bandwidth and then drain the queue, and also helps in converging toward a fair allocation of bandwidth. And then when the queue seems to be low enough based on the ECN signals we're getting, we then do a small additive increase and then continue in the BBR bandwidth probing growth curve. And this is a sort of approach that's been discussed before. You know, there's the Google Timely paper from 2015 discusses this kind of approach, and I also believe Bob Briscoe has done some work in this area for TCP Prague, if I'm not mistaken. And the picture here just sort of gives you an intuition about the dynamics that we'd like to see, where all of the flows are matching their pacing rate to the available bandwidth of the bottleneck link, so you can try to reduce the queuing there at the bottleneck. Next slide, please. So this slide has some details about the the mechanisms that we're experimenting with in the BBR version 2 codebase. And at the top, there's a sort of summary of the core mechanism as ECN marks are arriving once per round trip time. BBR v2 has thus far been reducing its in-flight cap or in-flight low multiplicatively based on an exponentially weighted moving average of the ECN mark rate. And then for this experimental variation, we are also capping the pacing rate or bandwidth low, as we call it in the code base, and decreasing that likewise. And the other sort of pieces of the puzzle here, as mentioned before, we're cutting the bandwidth low multiplicatively, and we're as another piece of this, we're increasing the ECN factor, which is the sort of magnitude or scaling factor for scaling the ECN response into the pacing and in-flight response. And then we're also decoupling the bandwidth high parameter, which was already existing in the BBR v2 model, from the maximum bandwidth sample that we've seen, so that we're sort of refining the notion of this bandwidth high parameter, whereas before it was just the maximum bandwidth that we've seen recently, and now we're turning it into a more refined notion that says it's tracking the maximum bandwidth that seems consistent with the tolerable level of ECN and loss marks. And if we're not seeing a tolerable level of those signals, then we do a multiplicative cut in the parameter. And then finally, when it seems like the level of queuing is low enough based on the ECN mark rate, then we go ahead and do a very small additive increase and then continue on in the bandwidth probing state machine. So those are just to give you a sense of the details. Next slide, please. So I'll present some synthetic lab test results to give a sense of the properties of the experimental algorithm here. Here we have 2 sender machines and 1 receiver, all in the same switch, all with a 50 gigabit NIC. And the switch here is configured to use DC-TCP style ECN marking, where the congestion experience bit is set if and only if the instantaneous queue is greater than 80 kilobytes in this particular case. And we've got 60-second bulk netperf transfers here. And we've collected a number of typical metrics, which I'll go through as I talk about the results. And then we're comparing 3 different congestion control variants here. One is the Linux DC-TCP code, the very latest. And then one is the BBR version 2 baseline, which is the algorithm without the changes I just described. And then BBR2 new is the algorithm with the changes I just described. Next slide, please. All right, so here are the results. Next slide. So the most interesting metric here in these experiments is that if we look at the queuing pressure as reflected in the retransmission rate, as we scale up the number of flows, notice this, we're sort of doubling the number of flows in each experiment. You can see with a small number of flows, all of the algorithms are doing quite good at keeping retransmission rate low. And as more flows are added, there's sort of varying degrees of retransmission rates. And with the largest number of flows, you can see DC-TCP, because it's necessarily running window limited, tends to have a fairly high retransmission rate, around 16% in this experiment. And the newer version of BBR is able to keep the queuing pressure lower and has a lower retransmission rate of around 1.6%. Next slide, please. Similarly, if we look at other metrics that reflect the queuing pressure, we can see that the newer version of BBR is doing a slightly better job at keeping the queues low. This is the average RTT. Next slide. And here's the 95th percentile RTT. It's sort of a similar pattern. Next slide, please. And then the throughputs are relatively similar for the variants. The older version of BBR2 is not quite as high as the others, but otherwise they're fairly similar. Next slide, please. And then you can look at sort of the CE mark rate is sort of an interesting way to look at how good the algorithms are doing at avoiding saturating the signal they're using. You can see that BBR, the newer version of BBR, is doing reasonably well here. Next slide, please. And then finally, we also look at the fairness, the Jane Fairness Index. For the small number of flows, they're all doing quite well. With the larger number of flows, they're all not quite ideal, and there's definitely some room for improvement. And we'll be looking at improving that. But it looks to me like they're usably fair and all, in the same ballpark. But there's some work that we'll be doing in that area. Next slide, please. So wrapping up, next slide. So where are we in terms of the status of the code? So the performance improvements that I was just discussing, we pushed those to the Google BBR GitHub repo. You can follow the link there for instructions on how to check out and play with the code. As we mentioned in July, there's also a BBR version 2 implementation for Quick. You can follow the URL there. And we encourage folks to take the code for a spin, try it out, share any test results they have or packet traces, share any ideas about issues they run into or ways to improve the code. We're always looking for feedback from the community. And then we have links to the slides and video from previous IETFs. Next slide, please. So where are we in terms of the deployment status? We've got BBR version 2 running for a small percentage of users on YouTube, where we see lower queuing delays than both BBR version 1 and Cubic, and considerably reduced packet loss, closer to Cubic than BBR version 1. And then we're in the process of a large-scale test pilot program pushing BBR v2 out as the default congestion control for TCP within and between Google data centers. And we're seeing some nice results there. And we're continuing to iterate both in production and lab tests. Next slide, please. So finally, in summary, we're actively working on BBR version 2 at Google and doing some tuning of performance, especially in data center contexts, high-speed data center networks, so that we can enable BBR version 2 globally at Google for internal traffic. And we're working, as you saw, on improving the algorithm to scale to larger numbers of flows. And as always, we invite the community to share any test results or issues or patches or ideas they have. We also wanted to give a shout out to the FreeBSD TCP community and the team at Netflix, which has been working on BBR, and they actually released an implementation of BBR version 1 for FreeBSD a couple of weeks ago. And we wanted to finally leave you with some food for thought. There's sort of an interesting question of, if you had to design a KPI or a key performance indicator for congestion control, what would that look like? And basically, the question is, how would you tell if your congestion control is doing well in a production environment, given that in a production environment, the traffic is dynamic, the routing is dynamic, topologies are dynamic, and so it's non-trivial, as far as we can tell, to develop a good key performance indicator, and we encourage folks to tackle that as a research problem if they're interested, because we think it's a valuable area for contributions. So thank you very much. Any questions or comments?
Hi, Neil. Martin Duke, F5. Thanks for giving up your Sunday night.
Yeah.
I have two questions. One is there a plan to update the BBR draft at some point? We are trying to track with an independent implementation. I know, obviously, Netflix as well. It'd be really nice to have a fixed target.
Yeah, an update of the internet draft to reflect version 2 is absolutely on the to-do list, and I apologize we weren't able to get it done by this IETF, but rest assured that it's definitely on the to-do list. Yeah.
Okay, thanks. The second, can you return to the sequence number graph you had? Yeah. So maybe I'm missing something here. So this strikes me as certainly for legacy TCP congestion controls, this is a feature, not a bug. Like you're not pulling more data out of the system when the app is not able to consume it. Is this a problem in BBR just because the ACK pacing messes up your BBR, your bandwidth estimation?
No, I don't think so. It turned out to be a problem in practice in these RPC workloads, and it showed up in the tail latencies for one of our storage applications that we're benchmarking. So we could definitely go into detail offline if that would be helpful. Yeah, I'm not sure what else to add at this point.
Okay. Well, I mean, I guess I think you were proposing that maybe this should just be a blanket change to TCP to remove that second condition about the window increase. And I don't have a lot of experience. I mean, I don't remember why exactly that was put in, but it strikes me as a fairly obvious thing for the reason I just said, which is to not just pile more stuff on a backlogged client, on a backlogged receiver.
Right. I mean, I think there are probably a number of trade-offs here, and I guess at the end of the day, maybe it's something that is going to be context dependent, whether it's an improvement or not. And so that's why we haven't offered it immediately as a fix for upstream. We want to get some experience with it in production workloads and see if it is. See if it is a net win. We think that we have good reason to believe that it will be at least acceptable, if not an improvement in every case, because the previous congestion control that was deployed in Google actually had a de facto behavior that in congested cases actually did essentially bypass check number 2. So we do have a fair amount of experience, at least in the congested case, with it helping. But we'll reserve final judgment until we've pushed this for all of our workloads, and we don't see any regressions.
Thanks, Neil.
I'm going to inject myself in the line right there just to ask a follow-up question. Do you know why that second condition is there in the kernel right now?
We don't know for sure. I mean, as Martin said, there is an argument that you can make about trying not to overload the receiver. Another argument that Eric Dumazet pointed out was that this check works nicely with the sender side fast path, which is only taken if the receive window is constant. And so this can save some CPU on the sender side if the receive window stays constant. Yeah, but this check predates the Git history in Linux, so it's a little tough to tell.
Wow. All right. Well, thank you.
So I'm very amused, of course, because my question was what was condition 2 expected to help solve.
Roberto, who are you?
Hi, I'm Roberto, and I'm with Facebook right now. One comment is say hi to everybody. The other comment is I love the data-driven approach, and in cases where there is no clear answer why, I'm really hoping that you will be able to drive changes in behavior. This particular one with number 2 here seems exceptionally odd to me because it provides a cliff of behavior. And we know cliffs in control theory tend to be bad for being able to understand the systemic properties. So I think it's super awesome to try and either eliminate 2 or prove that there's a good reason for it to exist, given that nobody seems to know why. So anyway, thank you.
Thank you.
Praveen, Microsoft, I had a couple of questions. So the minimum congestion window of 4. So TCP traditionally had that value at 1. My understanding is Quick is using 2 because of the problem that you mentioned in the slide. I'm just curious why you would pick 4 instead of 2.
So the details have to do with the dynamics that you get into given the delayed ACK behavior. So the basic idea is that you want to have 4 packets in flight so that 2 of those packets, well, the simplest scenario to imagine is basically that 2 of those packets are in flight in the data transmission direction. And because you have 2 of them, that's going to force out quickly force out a delayed ACK, or quickly force out an ACK immediately rather than delaying the ACK rather. So then you've got also 2 packets worth of budget coming back in the reverse direction in the form of acknowledgements, so that those packets, when those ACKs, when they arrive at the sender, they can immediately release the next 2 data packets. And you basically want to have all 4 packets worth of budget in flight so that there's always data going in the transmission direction and always ACKs flowing in the reverse direction. And the only way you can sort of ensure that that happens is if the receiver is acknowledging every other packet, is to have 4 ACKs, or sorry, 4 packets worth of budget in flight. Yeah, so obviously there's that does increase the aggregate in flight in these sorts of scenarios, but I think architecturally my sense would be that a better solution is ensuring that the flows tend to run pacing limited, because that's a more complete solution. And you're always going to have, no matter what your minimum C wind is, there's always going to be, if you're running window limited, there's always going to be some number of flows and some BDPs at which you get into trouble. So it seems like a more general fix is to run pacing limited with a minimum C wind that's robust.
Okay, I'm going to ask folks to be super quick because we are well over time at this point, and I'm closing the lines.
One more question was the target loss rate. So currently, how do you determine that for various workloads? Do you pick a constant value or do you tune it based on some parameters?
Right. So far, so far we are using a constant value in our deployment, but we are leaving the door open to making that something that could be conceivably tuned by deployments. For example, if you have a background file transfer, like a less than best effort transfer, you could, that is isolated to its own queue in your quality of service implementation in your switches, you might want to tolerate a higher loss rate, for example. But yeah, the final loss threshold that we'd like to target for the public internet is sort of yet to be determined, and we're open to ideas from the community about that. Yeah.
Thank you.
I came up here when you put up the thing about key performance indicators, which was quite a time ago now. Just to say to people, go and have a look at. There's a Hotnets paper in Hotnets this year called Beyond Jane's Fairness Index, which is quite an interesting set of thoughts on how to do that. Being Hotnets, obviously it's not completed work, but it's more about measuring the harm one flow causes others rather than equality. And on that conversation about sub-packet windows and things like that, I'm going to just forward reference to the slot about TCP Prague. Assad's finished his and defended his thesis in September on that work, and the code will be available hopefully before Thursday. And it's completed. We're just checking it out and everything. And I'll give a link to his thesis and things. But we did manage to get it working with a window-based algorithm inside the base TCP stack in Linux. Quite nicely, but there are other ways you can think about it. So I'd like to hear when we talk about it on Thursday more about it. Okay.
And just on that particular paper, we're going to have that presentation in Vancouver. I think the Hotnets paper.
Yoshi Nishida. I have very simple question. So you mentioned about documenting BBR v2, but I might be wrong, but my impression is BBR v2 consists of lots of small, complicated logic, and then some sounds like implementation tricks. And then, so I'm wondering how are you going to document spec of the BBR v2? So,
yes, as we mentioned with when Martin Duke came to the mic, we definitely intend to document the algorithm in an internet draft. Yeah.
But how, like a fast pass, something like fast pass seems to be an implementation trick from my point of view.
Right. So that is not something that would necessarily need to be in the draft because, as you say, that's an implementation detail. I think the much as the the traditional TCP fastpath is also not in the RFC 5681 spec. I don't think that the BBR fastpath would be in the internet draft, but I do think it's we definitely intend to document the high-level algorithm in the internet draft. Yeah.
Okay, sounds good. But if the implementation,
Yoshi, we have to move on. I'm sorry, Jake. I closed the lines earlier. Okay, last question. If you are still in the line before I closed it. So if you have 10 seconds.
Okay, Jonathan Norton. I'm just wanting to ask whether you cope well with RFC 3168 style ECN. For example, if ACK ECN is not negotiated.
Thus far, we're not planning on integrating BBR with RFC 3168 style ECN. We expect that thus far, people using BBR would not negotiate 3168 ECN. That's the current plan.
Thank you so much. I am going to thank Neil for staying up late and doing this. And I am hoping that we'll see the draft sooner than later. But we should talk offline about that, especially now that we're talking about adoption of documents in this research group. And thank you, Neil.
All right, thank you.
I'm going to now hand it off to Nitin Garg from Facebook, who's going to talk about their experiences with COPA.
Hello, everyone. Can you guys hear me? Should I move closer or further away? Closer is better. Okay. So yeah, a little bit about myself. My name is Nitin Garg. As you can see, it's my first IETF here. And I'm super excited to present some of the work we did at Facebook, comparing COPA with Cubic and BBR for live video upload use case. I work in the videos infrastructure team at Facebook. This is the rough outline of my presentation. I'll start with the motivation for our work. Then I'll go over the experiment setup we used and the results we saw on the application side. Then I'll do a brief overview of COPA, how that works, although that is not the focus of this presentation, but I think it's important to go over our understanding of COPA and how we applied it. And then in the end, I'll go over the conclusion and the future work that we have planned. So motivation. In videos infrastructure team, we work with a lot of product teams who work on videos, and we have realized that different type of video experiences require different quality and latency trade-off. So on one end of the spectrum, you have applications such as video calling, where the end-to-end glass-to-glass latency is super important. And these applications are usually willing to tolerate some quality loss in order to get that desired latency. On the other end of the spectrum, you have applications which don't care as much about latency, but they require extremely high quality playback. And then there are applications which fall in between, which are kind of like, yeah, we need low latency, but we also need high quality playback. So normally, you would need different type of congestion control algorithms compatible with different trade-off scenarios. What we wanted to find out was, is it possible for a single congestion control algorithm to offer a dial to the application, and the application could use that dial to just make it compatible with the desired quality versus latency trade-off. This is where we evaluated COPA, which is a delay-based congestion control algorithm. It has a dial, which is in the form of a parameter called delta, which you can use to control the delay sensitivity of the algorithm. So in our experiment setup, we wanted to start with something. So we started with one extreme where we are optimizing for throughput at the expense of delay. So we tuned COPA to optimize for throughput. And we did some comparisons with BBR and Cubic, which are two popular algorithms available. And for testing, we used the Facebook live streaming application. So in this application, any user with a mobile phone, they can go live. They can broadcast their live feed to their friends and followers. One thing to note here is that this is very different scenario as compared to HTTP style traffic. HTTP traffic could be short and bursty as well, could be app limited a lot of times as well. In this case, we have long running flows over a single quick connection, no multiplexing, with a mean duration of around 3 minutes. So you always have a constant flow of data which you are pushing over the wire. A different thing about this application is there is an adaptive bitrate algorithm running in the application, which would change the encoder bitrate in response to the network conditions. So as an example, if it sees that the network queues are building up and the throughput or the goodput it's seeing is lower, then it could change the encoder to produce less bytes. And hence that will result in less bytes being written on the wire. And we implemented COPA in the Facebook Quick library. Quick, because the transport is in user space, it allowed us to implement COPA quickly and experiment with it quickly. We used the BBR and Cubic implementations, which were already implemented and deployed for several other use cases with Quick. So for conducting the experiment, we used Facebook's A/B testing framework. So this framework allowed us to conduct this experiment all over the world. This framework helped us divide users into 3 random groups. One random group got COPA, the other group got BBR, and the third group got Cubic. We conducted this experiment for roughly 2 weeks, and we collected roughly 4 million samples in each group. So before diving into the results, I want to spend a little bit of time explaining the metrics and how we define them. So we mainly focused on 2 metrics on the application side to evaluate the congestion control algorithm. The one metric is average goodput. So the way we define it as you guys might already know, number of application bytes sent successfully over time. So because the broadcast could be long running, we calculated the total number of audio and video bytes that were sent during the entire broadcast. And then we divided that by the duration of the broadcast in seconds. That gives us average goodput. The second metric we used is average application observed RTT. This is our proxy for video ingest latency. To explain how this is calculated, there's a diagram here. To calculate this, the live streaming application inserts a ping frame with basically no payload, just a bunch of headers in between the audio and video data. Now that ping frame travels with the rest of the audio and video data through the transport, send buffer, through the kernel, through the same network, through the proxies, and it reaches the Facebook Live server, which is processing the audio and video data. When the server receives the ping frame, it immediately responds back with an acknowledgement frame for that ping frame, which goes all the way back to the live streaming application. Now the application uses the timing of sending the ping frame and getting the ACK. It calculates an RTT, which is its picture of what is the round trip time for the application. So the application does this measurement every second, and it gets roughly 1 sample every second. And to calculate average application observed RTT, we take the average of all of these samples. Now let's look at the results.
Clarification question, Nathan. So these are basically measured on the upload side? Yeah.
So looking at the results, for goodput, we saw that both COPA and BBR provided better goodput as compared to Cubic. However, we saw that COPA provided much better goodput as compared to BBR in our tests. To be specific, the P50 goodput was increased by 5% for BBR, and it increased by 16% for COPA. And similar trend followed even if you look at the worst connections, which have a lower quality. And as you can see, like at P90, it maxes out because our encoder bitrate is capped at 3 Mbps, because that's pretty much like a reasonable max quality that we want to have for our users. And this improvement was massive for us, and we also saw positive impact on some of the top line video metrics that we observe, which tell us how much people are watching those videos and how much people are engaging with those videos. The second metric we used is the video ingest latency, or application observed RTT. In this metric, what we saw was BBR was able to improve it slightly more for the best connections. So as you can see in the left graph, BBR reduced it. The BBR bar length is smaller. For P50, BBR reduced it by 8%, COPA reduced it by 4%. But those connections already had like quite low RTT, and the reduction was not as visible for our users. If you look at the worst connections, P75, P90 and above, COPA reductions were highest. For P90, COPA reduced the application RTT by 27%, whereas BBR application RTT was same as cubic in our tests. So this told us, so in the previous slide, you saw that COPA had better goodput. So that meant that COPA was able to help, like it helped transport to send more bytes successfully over the wire, and it also impacted the application ABR to produce more bytes in response to a better transport. But it was able to do it at the same time as keeping the latencies low, especially for the users like that had high latencies and where it mattered the most. So to be honest, like this result was quite surprising for us. We did not expect both goodput and latency to be better. So we spent some time trying to understand more like why that might be happening. So in the process, we found some interesting observations on the transport side. But before going into those, I want to spend some time explaining how COPA works. I'm sure a lot of you are already now aware, but I want to explain like how we applied it and how we understood it. So it's a tunable delay-based congestion control algorithm. The tunability part comes from the delta parameter, which varies from 0 to 1. The closer it is to 0, the more the algorithm will optimize for throughput. The closer it is to 1, the more it will optimize for delay. And it's a delay-based algorithm, which means it uses RTT variation as a signal of congestion and not loss or something else. In order to do that, it maintains two key variables. One is RTT minimum, which is the minimum RTT the flow has observed over a period of 10 seconds. It's estimate of the two-way propagation delay, which is a property of the network path. The second metric, the second variable it maintains is RTT standing. This is minimum RTT observed over a much smaller period, SRTT by 2 to be precise. This is COPA's estimate of what is the current round trip time, including any queuing delays in the bottleneck links. So the reason it chooses RTT by 2 is to make sure like the measurement is correct. If there are some jitters or there's ACK compression on the transport, which might mess up, which might make the algorithm think that there is queuing, even when there is not. Then it uses these two to calculate a queuing delay, which is RTT standing minus RTT minimum. So on every ACK, the algorithm, the main controller calculates the queuing delay, and then it calculates a target rate using this formula. The formula is 1 divided by delta times queuing delay. I'm not going to go in details of this. There is a long mathematical justification given in the paper. They show that like you can theoretically reach Nash equilibrium if you have certain modeling assumptions on the packet arrival pattern. So please do read more about it if you're interested. Then it compares the target rate with the current rate, and accordingly it adjusts the congestion window towards it by using an additive increase, additive decrease of variant. So it moves it by a V divided by delta times congestion window. So congestion window factor in the denominator helps ensure that the change in 1 RTT is going to be at max V divided by delta packets. V here is a velocity parameter. It is 1 by default. And this parameter comes in handy when COPA detects that it has been trying to converge towards a target rate for far too long, and it needs to do a better job at converging at it faster. In that case, it starts doubling the velocity parameter, I think, every RTT. The other unique thing or different thing about this algorithm is that it has a competitive mode. Normally, delay-based congestion control algorithms excuse me, will lose in the presence of buffer filling flows in the bottleneck link, and because if the buffers are filling up for no fault of the delay-based sender, then the delay-based sender will think that there's congestion or the delays are building up and it's going to back off before the loss-based flows are going to back off. Hence, it loses some of the throughput. COPA gets around this problem by using something called a competitive mode. So in competitive mode, it uses a heuristic, which I will explain a little bit more in the next slide, to detect the presence of buffer filling flows. And if it detects a buffer filling flow, then it adjusts the delta to be more aggressive, basically optimize more for throughput and perform better in the as compared to buffer filling flows. However, in our experimentation, we did not implement competitive mode. We wanted our experiment to be like smaller in scope. So we just tested like what will happen if you use aggressive value of delta without using competitive mode. So this is the steady state dynamics of COPA algorithm. This is what the bottleneck queue looks like in steady state. So the bottleneck queue oscillates between having 0 packets to 2.5 times delta inverse packets. And the entire pattern repeats itself every 5 RTT. So what I was saying before was that the competitive mode and competing flow detection. So COPA actually exploits this property that the queue is going to empty every 5 RTT. And if it's not doing that, then it thinks that there is a buffer filling flow which is preventing this from happening. So hence it concludes that there is a buffer filling flow in sharing the bottleneck link. So here, like if you see, let's say at t equal to 0, the queue starts to increase for the first time. So it will take about half RTT for the RTT standing measurement to be available and the target rate to reflect this change. And the target rate will be lower than the current rate at that time. Because of the inherent RTT delay in the network, it will take 1 RTT for that change to be effective. Basically, the change of reducing the target rate. And then in another RTT, the queues will start to drain again. And then the entire cycle repeats itself, like half RTT for the RTT standing measurement to reflect the change. And then another RTT for the congestion window increase or the target rate increase to result in the queue length to start increasing. In our experiment, and then the results that I'm presenting, they used a delta value of 0.04, which means roughly 25 packets in the equilibrium, 25 packets equilibrium queue length, and the maximum queue length is like 2.5 times 25. Now let's look at some of the transport level stuff we observed. So one metric we looked at is how is the transport RTT varying. So we saw, so this is measured as just taking the average of all the quick RTT measurements over the duration of the broadcast. So the trend we saw was very similar, kind of similar to application RTT measurement. BBR for the best connections, which already had pretty low RTT, BBR was able to reduce it slightly more as compared to COPA and Cubic. However, if you look at the tail cases, 75, 90, 95, COPA reductions were way higher as compared to BBR. So for P90, for example, COPA reduced the RTT by 38%, whereas BBR reduced it by 8.8%. So this was pretty good to see. And this told us a little bit like where the application RTT reductions might be coming from. And it also showed us that like COPA flow is not just improving the application latency, but it's also improving the RTT for the network. So if there are any other flows which are also sharing the bottleneck link, like they will also start seeing a lower RTTs. The other metric we looked at is retransmission overhead. So we defined it as the total number of bytes retransmitted by the transport during the course of the broadcast divided by total number of bytes acknowledged during the course of the broadcast. I think it's a pretty important metric to look at because it tells you how efficient the transport is. If you are wasting resources and bandwidth rewriting the same bytes over the wire again and again, it's just not good for anyone. So what we found here was that for 90% of users, COPA retransmission overhead was way lower as compared to both BBR and Cubic. It was about half of what BBR had and around 1/4 of what Cubic had. So this gave us an idea like why application goodput might have been better. Like this might be one of the reasons why we were able to send more bytes successfully for the application. However, for the last 10% of users, we saw a different trend that COPA retransmission overhead grew very rapidly and it became 3 to 4 times as compared to COPA and Cubic and BBR, which was concerning as well as surprising because we did not see a corresponding proportional degradation in the application metrics for any of the tail users. So we spent some time debugging into it, and the first thing we did was we sampled a few cases, some broadcasts, which had a very high loss rate for COPA. So we noticed two things. One thing was that these flows had very constant throughput. As you can see by the red line here, the number of bytes act over time, it's a straight line. And the second thing we observed is that these flows actually have very low RTTs. So in this sample, except the one spike, the RTT stays constant around 75 milliseconds. So this did not look like congestion or losses happening because of buffers filling up. This looked more like network policing to us, because if there's a token bucket, a policer in effect, which is identifying your traffic and limiting it at a bit rate, it's not going to result in any increase in queuing delays or RTTs, but it will look more like this. We also grouped our retransmission overhead numbers by ASN, and we found that they do vary greatly depending on which ASN you're looking at. Some ASNs which are known to police Facebook traffic, they had way higher retransmission overhead for tail cases for COPA, and there were some other ASNs where the retransmission overheads looked very similar. So to generalize our finding, we did some more aggregated analysis. We looked at the relationship between our retransmission overhead and RTT queuing delays. And we found that for cubic, they are highly correlated. As the retransmission overhead increases, RTT and queuing delays also increase for cubic, which indicates that all the losses are happening because of congestion. But for COPA, we saw similar trend for the first part of the graph. But later on, we see that as the retransmission overhead increases, the RTTs and queuing delays actually start to come down. So this kind of solidified our hypothesis that the network policing is a big factor playing a role here in the high retransmissions. Although it's also possible that there are some other reasons at play here, and network policing is not the only one. For example, short buffers. If there's a short buffer and COPA sender is trying to maintain an equilibrium queue length of 25 packets, then if the buffer is smaller than that, then you're definitely going to run into losses. So definitely there are improvements possible in COPA to handle this case better. Competitive mode, as I described before, could help because it could adjust the target delta based on whether it sees loss or success. We could also add a heuristic to change congestion window based on loss, something simple like multiplicative decrease based on target loss, just like Cubic or Reno or even BBR now is doing. Other option is to have an explicit network policer detection similar to how BBR V1 had it. So in conclusion, the aggregated results showed us that COPA provided better quality and lower latencies in our tests. These tests were for mobile broadcasts, for uploads, and we compared with Cubic and BBR with Quick. But one thing to note is BBR, we are tuning BBR in our internal implementation, and also BBR V2 is happening, so the results may differ in future. One of the big future work items is a better understanding of the reasons behind these improvements. Are these improvements because of lower retransmission overhead? Or is it because COPA is just doing better target rate estimation by sending fewer packets and it's converging to that faster? Or it could be something else. In the beginning of presentation, I spoke about our goal of having a tunable delay-based congestion control algorithm, which could be compatible with all the video experiences. And so far, we only ran experiments on one extreme where we are optimizing for throughput. We would also like to run some experiments with with Google congestion control as a comparison, where the end-to-end ultra-low latency is super important. And we would also like to test for more use cases like playback and download traffic. These are a few links where you can read and learn more. My email is here, and I'm happy to answer any questions now or offline.
Thank you so much, Nitin. I'll inject myself in the front of the queue. So I'm asking this question from the floor, basically. The scenario that you're using this under right now is when the client is uploading video up to the server, and this is almost a textbook example of a situation where there is no cross traffic or there's no other traffic that is going to be competing with COPA at a bottleneck. Because I imagine that when people are uploading video, they're not doing anything else on the phone. So it seems to make sense that even without the competitive mode, which I like to think of as TCP friendly mode, because that's what it is,
Not TCP friendly, but
no, that's what Cubic calls it, but we won't get there. The point is that that's simply it makes sense that it works without that. So I'd be interested in seeing more evaluation on what happens when you have competition with Cubic, with BBR, with other things in the network, because that's going to be useful for download streams.
Right.
And in the common case, that's going to be an important factor.
Definitely, that's like I said, that's one of the future work items. Although, to be honest, when we started working on this, we did not really know that there is going to be no competing traffic, and even now, I'm not totally sure if there is any evidence, a real life evidence of that. I would love to read more about it. I know from textbook that it is the case, but this is one of the future work items.
Thank you, Michael.
Michael Welzel. I'll begin by saying that I greatly appreciate Facebook coming here and bringing this here, and you had some good results, and I guess the mechanism is not altogether unreasonable. I have to say, sorry for that, but I have to say that the base idea that this is based upon of a delta that reflects a trade-off between having high delay and good throughput, or low delay and not so much throughput, is fundamentally wrong. Just because, if you look at the base intuition between mechanisms like BBR or L4S or things like that, they aim at having high throughput and having a low queue. And having a large queue just isn't good for anybody. I think there is such a trade-off when you're trying to compete with TCP. So there is, you had this in your competitive mode. You can try to be a bit more or less aggressive, which will produce more or less queuing. So I guess there you have the trade-off. But whenever you are able to detect that there isn't any other traffic competing with you, I don't think the idea of including such a trade-off in the design as a base idea is good at all.
So my answer to that is maybe you're right. I don't know for sure. But the trade-off does exist on the product side, because on the other hand, we have video calling applications which have not been able to use Cubic or BBR so far as I know. They have to use something like Google Congestion Control, where they have to really optimize for end-to-end delays, right? On the transport side, we did run some limited experiments by using a very high value of a delta, right? And I did see that queuing delays decreased even more. So, I don't know, fundamentally if it's a good idea or not, but from the application point of view, there's definitely a trade-off. And if the congestion control could also kind of give you a varying performance depending on it could also be expressed in a different way. For example, prop rate exposes a target delay to the application, and it will just try to optimize and limit the queue, the bottleneck queue delay to that. That could be an alternative way for application to benefit from it. I honestly don't know.
Yeah, I can maybe point you at some other work offline.
Yeah, totally.
Okay.
Stuart Cheshire from Apple. You presented some results showing marginally better application throughput, which is interesting. I think it would be interesting to understand where that's coming from, because either the other congestion control algorithms were letting the line go idle and wasting capacity, or they were retransmitting unnecessarily and wasting capacity with duplicates, or something else. And it would be really interesting to know where that extra is coming from.
Yeah, I agree with you.
Praveen, Microsoft. Were these tests done on Wi-Fi links or LTE?
Good question. So we ran these tests globally. And when I looked at the data, about 3/4 of the users were using cellular. I don't know LTE versus 3G or something else. And about 1/4 were using Wi-Fi.
But in the Wi-Fi case, there would be competing traffic at the bottleneck link, because it would be probably the first hop of the ISP or something.
Probably,
right?
yeah. And when I looked at the results and compared them, the trend was similar for Wi-Fi and cellular, although we saw more wins on cellular as compared to Wi-Fi.
And what is the delta value for these experiments that you?
0.04.
Thank you.
Roberto Peon. I just wanted to push back on delay versus bandwidth not making sense. I also want to agree with delay versus bandwidth not making sense. I'm holding both of these opinions simultaneously because it's hard to define what the network is. Does the network is the boundary of the network between the application and the operating system, or is it between the NIC sending packets and the fabric to another NIC, right? Depending on where we are in the stack, we tend to think of either of these as the network and try to exclude one of the others, generally the internal to the host part. So we know from a previous presentation by Neil Cardwell, for instance, that there are parts of the stack that are trying to reduce the amount of overhead that we are experiencing within the host. And the effort by which we do this, and of course there's nagels, et cetera, right? The effort by which we do this is really a trade-off of how expensive it is in CPU versus how important it is to get the information through. So there you go. Sorry.
Thank you.
Thank you so much, folks. And I want to thank Nitin for showing up here and presenting this. Please make him feel welcome. It's his first IETF/IRTF/ICCRG meeting. And for everybody else watching, I'd love to see more presentations like this. If you're doing any experiments in your house or in your lab or at your company, come share them with us. And we'll now move on to Marcus and get this up. MCDCCP. There you go. Take it away.
Good morning. My name is Markus Arment from Deutsche Telekom, and today I want to present some joint work with Caltech University and City University London on multipath DCCP that we intend to use for providing multipath capabilities for UDP and IP traffic. Why I want to present it today here at ICCRG is that we see a challenge there in respect to congestion control, and I think you are the right group to become aware of this and maybe work together with us on a solution. And we also think that this is not a limited issue to the multipath DCCP. Maybe that is also something which affects in future the quick community. We come to this during the presentation. First of all, I want to give you a short introduction. Why are we working on multipath DCCP? What is the reason behind? I want to make you aware about the development we did so far. And then coming quickly to the point where we see the issue of congestion control. The multipath DCCP as such is usually pushed at TSVWG, where we also have some updates in the afternoon session. Okay, starting with motivation, why are we working on a solution for providing multipath capabilities to UDP or IP traffic? So as you may know, there are specifications ongoing in the 3GPP area and also in the BBF Broadband Forum on multi-connectivity architectures to provide multipath usage to either mobile phones, though that is on the upper part, that is directly happening at 3GPP, release 16, so within the 5G standardization, and they're discussed in the area of ATSSS, access traffic steering switching splitting. It's an operator-controlled approach, so that's why we as Deutsche Telekom are very interested in that. That means multi-connectivity is terminated in the operator network. The same is also happening for the hybrid access use case, where multi-connectivity is applied between a multi-path capable CPE using cellular and fixed access, and again the operator network. In future, the hybrid access will most probably also rely on the 3GPP ATSSS specification. And currently in release 16, multipath TCP is a protocol which is defined for making simultaneous use of multiple access. If we start now with having a look on how the traffic mix has changed over the last years, I think I don't tell you something new. We see that the quick traffic is coming up more and more. So that is some statistic from our fixed network in 2018, where we already see more or less 12% of quick traffic, and we think with HTTP3 deployment, this will become more and more, and maybe it comes to the point where quick or UDP traffic in future dominate the TCP. So that is totally different to what we have seen maybe 3, 4, or 5 years ago, where TCP were the dominating protocol with almost 100%, with almost 100% share. But coming now back to these multi-connectivity architectures we have seen before within the ATSSS, where multipath TCP is the protocol for providing multipath transmission. This means that it cannot cover anymore all the traffic which is today generated between customers and the internet, because the quick is coming. So our findings so far is we have a long-lasting experience with multipath TCP. It's a very well working protocol. It's efficient. It's a good candidate to use or to provide multi-connectivity services. And there's also a finding that the congestion control shipped by TCP and also used within multipath TCP for scheduling decisions and so on is very beneficial. Another finding is, so far, if you look at IETF, for example, there's no multipath protocol for UDP or IP traffic. And an encapsulation into multipath TCP of such protocols is not an option. At least that is our opinion, and that was also something discussed years ago in the multipath TCP mailing list, that this does not make sense, because if you encapsulate UDP or IP traffic into multipath TCP, then you impose the reliable nature of TCP. So a potential multipath solution for UDP or even IP traffic must not impose TCP-like reliability, additional high latency, packet scrambling, or head-of-line blocking. Otherwise, it breaks the UDP and IP principles on transportation and service expectations. Before I come now to the solution and talk about the multipath TCP itself, I want to present what are the key components for a multipath transmission. For sure, you have a generator and a receiver part. In between, you have multiple paths or multiple accesses, so at least more than one path to provide multi-connectivity. And you need a scheduling unit to distribute traffic over multiple paths. And it is very beneficial to have a path estimation for the scheduling unit, which gives you information about the path characteristic, latencies, data rate, available capacities, so that the scheduling unit can make proper decisions, efficient decisions. Does not overload the path, maybe according to policies, preferring path with low latencies. It needs this information, which latencies are applied to the individual path. And last but not least, you also, in most scenarios and real scenarios, you need some reorder queue to compensate the different path characteristics, to compensate the latency differences, and so on. For this reordering unit, or for making this reordering working. For sure, you need also some sequencing, but that is very simple as such. So the most critical components I see are the scheduling, the path estimation, and the reordering. So all of this has worked together to make efficient multipath usage possible. Now coming to the solution, multipath DCCP. So we had a look at the IETF, which types of protocols are available, which can support us in finding a solution to transport UDP or IP traffic over multiple paths. And there we came up with the DCCP protocol, which is a mix between TCP and UDP. It's of an unreliable nature, but it has a congestion control. And that we think we can exploit for our purposes. So what we imagine is we have the multipath DCCP as such, which by itself is only possible to distribute DCCP traffic over multiple paths. But if you combine it with a multipath framework, which more or less means we have virtual network interfaces, which can consume any kind of IP traffic, and the traffic which is incoming into these virtual network interfaces then encapsulated into the multipath DCCP, distributed, and then on receiver side again maybe reordered, and then stripped all the DCCP information and sent out of the outgoing virtual network interface. So that is a rough description of how we imagine a solution. You can find more details in all the drafts I have mentioned here on the slide. And that is our prototype and also our simulation testbed we have available. So we have a Linux kernel implementation extending the available DCCP protocol by multipath capability. And the same we have available in NF3 for simulation purposes. It's the sender side. You can see on the left side the multipath DCCP home gateway, as we have called it, and that is very similar to multipath TCP. We have a modular scheduler which can load different kind of scheduling algorithms, round robin, for example, cheapest pipe first, which is a path prioritization scheduler, but also more sophisticated OTRs, for example, out of order for in-order arrival scheduler. On receiver side, and that is something new compared to multipath TCP, we have reordering modules, so we can apply different kind of reordering mechanisms. We have a passive one, which more or less does nothing. We have a adaptive fixed algorithm, which waits for a fixed time when packets are missed, and then skips possible gaps in the reordering queue. We have adaptive active, so that is a dynamic approach using the RTT or the latency information from the congestion control to adapt in time. And last but not least, we have delay equalization, which is more or less no reordering approach. It just tries to delay the packet on the faster path by the latency difference. We have a path manager. We have this virtual network interfaces from the multipath framework implemented. So it's a more or less complete setup which we can use for testing. Presenting now some results in short. That is really a short excerpt of results, just to make you aware what is already working, and then coming to the challenge we see. So that is our NF3 setup. where you see that we have plenty of possibilities. We can simulate different UEs. We can simulate eNote B or cellular access. We can simulate Wi-Fi access. And also we can simulate moving scenarios where we move UEs from one point to the other, which maybe lead to the fact, and therefore I have results in the next slide, that we lose connectivity or that we enter new access nodes and we can get connectivity. So that are results from last IETF, but again, just to remember you, so switching and aggregation is possible with our multipass DCCP setup. So on the top, you see when we move a UE out of a Wi-Fi access, so that the Wi-Fi access is not available anymore, then the UE automatically connects to the LTE, and the multipass DCCP is capable of doing this in a seamless way. And with a pure switching approach, you see between switching from Wi-Fi to cellular, you have a gap. With aggregation mode, which is also supported by multipass DCCP, you see a more or less seamless handover without having a gap between switching from Wi-Fi to LTE. We think that is a very beneficial scenario. The same test we also did, and we think that is very realistic. Maybe I have to switch back. So that was with pure UDP traffic. It was some iPerf UDP traffic we generated, but that is not very realistic. So we did the same test with UDP combined with NADA congestion control. Most of the UDP traffic we see in the field is to some extent congestion controlled. And if you talk about quick, then it's pretty clear that this is congestion controlled. And you see here in the same scenario, switching or aggregation, it also works to some extent, but you see some interaction between the NADA congestion control and also the DCCP congestion control. You have this black reference line. So that is from the previous slide, the results, where you have seen more or less, where you have seen that after switching from one access to the other, a direct use of the full capacity was possible, whereas now with the NADA controlled UDP traffic, you see it takes some time to adapt. This one I will skip for time reasons. That is now also exploring a little bit what's going on in terms of delay. That is also some result from last IETF, where we proved that reordering makes sense. We need reordering in a multipass setup supporting UDP traffic. And the green bar here, that is proving that reordering is beneficial over scenarios without reordering. You can find the details in the slides from last IETF. What is new? We have some real-world results with YouTube traffic based on the QUIC protocol now. You see here the setup. We have the multipass DCCP client and multipass DCCP server. That is a local setup, but connected to the internet. Connected to the multipass DCCP client, we have a laptop running the Chrome browser. And between the both multipass DCCP boxes, we have two links, two Ethernet links, going through so-called TC boxes with which we can shape the links and where we can change the path characteristics. As I said, we use the Chrome browser. With that, we are able to request YouTube videos using the Iccrg protocol. We requested a static video with a fixed resolution, and we skipped this video at 10, 30, 50, 70, 90, and 110 seconds to force buffering. The total duration of the test were 120 seconds. And the network conditions changed at 60 seconds, that we see on the next slide again. So we had two paths, both at 1 megabit per second and a latency of 10 on the first path and 50 milliseconds on the second path. After 60 seconds, we changed from 10 to 90 milliseconds on the first path. And on the right side, you can see the playback ratio versus the data rate, where you can see that the green circles that are the one using multipath in combination with reordering promises the highest gain, whereas other scenarios like single path usage or multipath DCCP without reordering have some lower playback ratio compared to this multipath usage with reordering. However, that is not part of this slide. A detailed evaluation revealed the imperfect path usage, even in the best performing use case, which means even if we have reordering and multipath usage combined, there is still some room to improve the customer experience. And now coming to an intermediate conclusion before coming later to the final conclusion. So our multipath DCCP prototype and also the standards or the drafts we have available at TSV-WG, making very clear that this is something which can work, scheduling profits from the DCCP congestion control, and can therefore perform similar to multipath TCP. The reordering on receiver side is proved mandatory for efficient multipath transmission of unreliable traffic. Smart algorithms to keep the traffic flow smoothly ongoing are required and can make use of congestion control information. Head of line blocking is not purposeful and should always assess if it is worth to wait for missing out of order information, which means encapsulation into multipath TCP doesn't make sense for UDP or IP traffic. You have also seen that we have plenty of scheduling and reordering algorithms in our prototype. And all of this together benefits from the congestion control shipped with DCCP. So from this perspective, it was a very clever decision to use the DCCP. And also with the congestion control, we can make sure that we do not overload path, so that we do not force a packet loss. However, the main target protocols transmitted over the multipath TCP framework, like Iccrg, employ an own congestion control. In combination with multipath TCP, this leads to a kind of congestion control over congestion control scenario with well-known issues from literature. So that is now the point where I think it becomes very interesting for ICCRG. So in all of our tests, we used so far the CCID2, which is a TCP-like congestion control. We ask ourselves if it makes sense to use CCID2, what could be the alternative, and how in general we tackle the problem of congestion control over congestion control in such scenarios if we assume that congestion control for multipass purposes is the right way to go.
Marcus,
we are
time check. Do you?
Yeah, I see. Okay.
That's what I would recommend.
Yeah. Coming directly to the conclusion. So as I said, we have this issue of congestion control over congestion control identified. We think also that affect the quick community. So there are drafts regarding quick tunneling, where at the end you have the same question, depending on which type of traffic you want to tunnel through quick. My main question today is ICCRG the right place? And for dealing with this question of congestion control over congestion control, and who is interested in elaborating this topic further? Not dedicated to this multipass TCP. I think it's a general question, but for sure it would help us in pushing the multipass TCP further.
Thank you for your presentation, Marcus. I think just very quickly to answer the question about is this ICCRG the right place? It can be, is the short answer that I have. I think the question I would have is, are there other folks who are interested in this problem? And I'm not just speaking academically. Is this a real problem? Are folks interested in deploying? Are they facing this problem in production? That sort of question. If you can, you could have this conversation on the mailing list and see if there are people who are interested in working with you on establishing relevance. Any other questions? We have minus.
Yoshi Nishida, a quick question. Have you ever experimented with that path is not disjoint? No. For example, if some multipass DCC subflows share the same bottleneck. Have you ever experimented with that kind of environment?
The question was if we experimented with coupled congestion control like multipass TCP uses. Right. No, that is on our to-do list. But I'm not sure. At the end, it also ends up in congestion control over congestion control. For sure, we have to do this, or we should do such tests. What we have done, but what was not able to show up, that we have implemented BBR for DCCP, and we did some tests with that. That was very promising, but coupled congestion control is on our to-do list. We have the issue that we have to port everything into the DCCP world to make such tests.
Okay. Yeah, but I think that's important metric.
Yeah, sure. It's on our to-do list. But again, the problem stays at the end. Then we have inner congestion control of the piggyback traffic, then over coupled congestion control, where I also think that this ends up in some challenges or conflicts.
Thank you so much, Marcus. And with that, we'll end the session. I'm going to quickly note that in Vancouver, I'm trying to get together. There's been a recent spate of academic work on BBR analysis, so I'm going to try and get those authors and even Neil to show up, or BBR folks to show up in Vancouver. So I'm hoping to do 2 ICCRG sessions in Vancouver if all of those pan out. This is tentative, of course. One of them will be around BBR specifically, and the other one will be more generic. But if you have any work around that, if you have any analysis that you've been doing with BBR or BBR v2, please write to me. I'd love to have that be a part of the program. And with that, we'll end. Thank you so much. And I'll specifically thank Marcus for winding down his presentation quickly. And we'll see you in Vancouver. Thank you, folks.